Hello everyone, thanks for coming to my Grads 2021 presentation. The title of my presentation is An Algorithm for Measuring Landslide Deformation in LiDAR Point Clouds Using Trees. So we want to be able to measure the deformation of landslides that are occurring along infrastructure of interest, and a lot of times we use terrestrial LiDAR to do this, but it's difficult in certain situations where the landslides have movement directions that are inappropriate for the position of the LiDAR. So in this case, for an example of a translational landslide, if we do a traditional digital elevation model analysis, we get negative change at the top of the landslide, positive change at the bottom, but the direction of movement of the landslide is not actually accurately characterized here. For landslides that have vegetation on them, a recent paper suggested that we could track the trees that are extracted from our LiDAR data to get a better picture of the true movement vectors of the landslide itself. So what I did was I built on this idea of tracking landslides using the trees on the landslide in terrestrial LiDAR data, and I built a MATLAB and Cloud Compare based semi-automated workflow which extracts trees from LiDAR data, matches them through time, and then calculates their deformation. So this is an overview of the algorithm I developed. First of all, the point cloud from the terrestrial LiDAR scanner is classified to remove things that are not tree trunks. So that's illustrated in this first image here. Next, we cluster individual tree trunks so that we know one tree trunk from the next tree trunk. Third, we match corresponding tree trunks through time. So in this case, the same tree is matched between two different terrestrial LiDAR scans at two different times. And then from that, we use this thing called rototranslation analysis to calculate the rotation and movement of that tree over time, which is given as an indication of the movement and failure mechanisms of the landslide itself. So the first step in this process is classification to remove things that are not tree trunks from the data. So in this case, we tested 3 different methods for classifying individual points in the point clouds using geometric features, local neighborhood geometric features of the point cloud. We tested 3 different methods to accomplish this task. First one was a threshold of a single geometric feature. The second method was a decision tree with 4 different geometric features being incorporated. And the third was a machine learning algorithm called random forest, which incorporated over 50 different geometric features. And so these geometric features that we're looking at here look like things like linearity, how linear is the point cloud in a certain range, and how vertical is it, and how dense is it, etc. So what ended up happening was we compared several different methods of using these different algorithms, and what we found was that a simple 4-parameter decision tree ended up being almost just as accurate as the most complicated machine learning algorithm that we developed, around an accuracy of 85%. This up here, this diagram workflow is illustrating the decision tree and how that is able to distinguish between points that are not corresponding to trunks and those that are corresponding to trunks. So we ultimately decided to go with a simple 4-parameter decision tree that can be changed quickly to account for differences in different LiDAR scans taken at different distances from the slope, different tree species, and stuff like that, without needing to go through this whole machine learning analysis. analysis. The next step was to cluster individual tree trunks and distinguish them from one another in a scan. We used a MATLAB function that's designed and built to do this, did a sensitivity analysis on the distance parameter for that algorithm. Turns out that it's not particularly sensitive to the parameters, so these are just illustrating 3 different cases of that distance parameter, and we can see how they all more or less successfully cluster out individual trees. The next step is to figure out which trees are the same through time. So if we have a tree that is in one location at time 1, another location at time 2, we want to make sure that that is the same tree between both scans. The way we do this is by looking at nearest neighbor clusters and subjecting them to a series of 4 different matching criteria. The most important matching criteria turned out to be the root mean squared error of the alignment of the 2 clouds using something called an iterative closest point algorithm. And so with that and a few other parameters which don't have time to get into, we can distinguish with high accuracy between clouds that are a match and clouds that are not a match. So the one on the left is a match, it passes all of the matching criteria, and the 2 on the right are potential matches, but they don't pass the matching criteria, such as they don't have similar lengths, or they don't have similar enough or a low enough RMS error in this case. And so that's how we can distinguish between trees that are close to each other but are not actual matches. So we created a validation data set to check the accuracy of this matching step. And what we found was, depending on which combinations of matching parameters that were used, we get a precision of between 90 and 99%, indicating that if the user is looking at a set of results, they would expect between 9 and 10 and 99 out of 100 of extracted trees to be correct. And so this represents a very good result in terms of the algorithm's ability to extract a reasonable number of trees and not have a large number of false positives. So in this case, in the worst case, we had 113 true positives, so a lot of correctly extracted trees, and 11 false positive matches that were past the criteria but were not actual matches. So what this ultimately leads to is case studies where we apply this algorithm and understand the tree movement on a landslide. So this particular landslide is the case study that we developed the algorithm for and are demonstrating results on. And we had 6 different lidar scans for this landslide. And so this table shows 3 different time steps here where we selected slightly different parameters for the algorithm to adjust for differences in foliage arising from the season, the month that the scan was taken in. But generally speaking, these parameters don't need to be changed all that much through time to get good results. So what do the results look like? We can plot them in terms of sort of a map where each one of these dots in sort of a plan view, each one of these dots represents an extracted tree. The color represents the magnitude of movement, and the vector represents the direction of that movement. And we have 5 different time steps for this landslide. So we can see from this the spatial variability in the magnitude and direction of tree movements on this landslide. And we can also see how how this varies over time quite accurately. And so the next slide shows a better idea of the temporal variation in the movement of this landslide, where in the summer of 2018 there was a surge, and then less movement in the winter of 2018 to 2019, no movement essentially in 2019, and then another surge in 2020. So that gives us a very clear picture of the dynamics of this landslide over time. So that concludes the presentation. Feel free to reach out to me with my email, and the code for this algorithm is also available on my GitHub, also at the link provided. Thanks for listening.